Hi, welcome to this video. My name is Martin Sigley, and today we're going to be discussing decimal, binary, octal, hexadecimal, and conversion between these number systems. You can either watch this video in its entirety, or you may skip to any section that you wish to review. We will be performing this tutorial in this order. So, I hope that you enjoy this video, and thank you for watching. Hi, let's go ahead and begin by discussing decimal. Decimal has the digits 0 through 9. It is a base 10 or radix 10 number system. The base of the number system is always determined by the number of unique characters or number of unique numerals that will represent a number. In decimal we have 0 through 9. Those are 10 unique digits that can represent a number. Therefore, it is a base 10 or radix 10 number system. Let's go ahead and take a look at a number, 7,521. Now, to denote that this is a base 10 or radix 10 decimal number, you could place a small 10 on the bottom right corner of the number. If this were a hexadecimal number, for example, which is base 16, you could place a small 16 to let someone know that this would be a hexadecimal number. In this case, you're dealing with decimal. Each position, as we all know, has a positional weight. This is the ones place, the tens, the 100s, and the 1000s. Each one of these positions are powers of 10. 10 raised to the 0 power is equal to 1. 10 raised to the first power is equal to 10. 10 to the second is 100, and 10 to the third is 1000. What are powers? Powers are numbers that we multiplied by itself. So, if 10 is raised to the power of 2, that means 10 has been multiplied by itself. 10 times 10 equals 100. If we were to want to find this position, 100 times 10 equals 1000. To find the next positional weight, 1000 times 10 would equal 10,000, and so on. Now, each one of these digits corresponding with their positional weights, if we were to multiply this, we would have 1 times 1 is 1, 2 times 10 is 20, 5 times 100 is 500, and 7 times 1000 is equal to 7,000. Now, if we add all of these numbers together, 7,000 plus 500 plus 20 plus 1, we will get 7,521, the same number. This covers decimal. Thank you for watching, and I'll see you soon. Hi, now let's discuss binary. Binary means 2. Binary is a base or radix 2 number system. Base 2, radix 2. Binary has the digits 0 through 1. A base of a number system is always determined by the unique number of characters it has to represent a number. Binary has 0 and 1, which is 2 numbers, which makes it a base 2 radix 2 number system. Let's go ahead and take a look at a binary number. 1011. Each one of these digits or bits has a positional weight associated with it. This is going to be powers of 2. So 2 raised to the 0 power is always 1. Any non-zero number raised to the 0 power is always 1. 2 raised to the first power is always the same as the number as itself. So 2 raised to the first power is 2. 2 raised to the second power, that is 4. 2 raised to the third power, which is 8. Binary is the simplest of the weighted number systems. So instead of looking at it and thinking about powers, we could also say 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 4 is 8, 8 plus 8 is 16, 32, 64. And you can just double these numbers to find each next positional weight. Now, let's multiply each digit by its corresponding positional weight. 1 times 1 is 1. 1 times 2 is 2. 0 times 4 is 0. And 1 times 8 is 8. If we add all of these numbers together, we have 8, 9, 10, 11, 11 in decimal. Now, binary can also be denoted by placing a small 2 to the bottom right corner of the number. That will indicate in any number system what the radix or base of that number system is by this notation right here in the bottom right corner. Also, depending on the compiler, assembler, or interpreter that you're using, you could likely end up seeing a notation like a percentage sign right here. And this could also tell you that this would be a binary number in your particular software that you're using. And I believe that covers binary, and thank you for watching. Let's discuss octal. Octal has digits 0 through 7. It is a base 8 or radix 8 number system. Either of these terms can be used. The base of a number system is always determined by the number of unique characters used to represent a value. In this case, 0 through 7 equals 8 unique characters. So this is octal base 8 number system. Let's go ahead and take a look at a number. Let's say, no, 7. 7, 5, 2, 1. Okay, 7, 5, 2, 1 in octal, which is, we can also indicate right here with a notation of base 8 at the bottom right corner of the number, has positional weights, and the first one is 8 to the power 0, 8 to the first power, 8 to the second power, and 8 to the third power. Any number, non-zero number raised to the 0 power is equal to 1. Every number raised to the power of 1 is equal to itself, 8. And 8 to the second power is 8 times 8, which is 64. And 8 to the third power would be 64 times 8, which is 512. Now, if we take each one of these digits and we multiply them by their corresponding positional weight, we will have 1 times 1 is 1, 2 times 8 is 16. I'm going to go ahead and grab a calculator. I don't have a whole lot of board space. Let's see. 64 times 5 is equal to 320. And 7 times 512 is 3,584. Now, if we take these numbers and we were to add them together, 3,584 plus 320 plus 16 plus 1, we would have 3,921 in decimal. So 3,921 in decimal is the equivalent to 7521 in octal. Thank you for watching. Hi, let's discuss hexadecimal. Hexadecimal has digits ranging from 0 through 9 and A through F. A through F have corresponding numbers that they equal. A equals 10. B equals 11. C equals 12. D equals 13. E equals 14, and F equals 15. Now, the base of hexadecimal is 16, or the radix is 16. Base 16, or radix 16. The base of a number system is always determined by the number of unique characters used to represent a digit in that number system. So 0 through F is 16 unique characters, which makes it a 16 number system. Let's go ahead and take a look at a hexadecimal number. B, C, 1, 2. Base 16. Placing a small 16 notation at the bottom right corner will indicate that this is a base 16 hexadecimal number. Each digit has a positional weight associated with it. They are powers of 16. 16 to the 0 power is 1. Any non-zero number raised to the 0 power is always equal to 1. 16 raised to the first power, any number raised to the first power is equal to itself. 16 raised to the second power is 16 times 16, which is 256. 16 raised to the third power is 256 times 16, which is 4,096. Now, if we were to multiply each one of these digits by their corresponding positional weight, 2 times 1 is 2. 1 times 16 is 16. And with a calculator, I'm going to cheat. C is equal to 12, so 12 times 256 is equal to 3,072. And B is equal to 11. So 11 times 4,096 equals 45,056. Now, if we take all these numbers below and we add them together, $48,146 in decimal is the equivalent to BC12 in hexadecimal. Now, depending on the interpreter, compiler, or assembler that you're using, you could see another way to denote a hexadecimal number. One popular way is placing a 0 and a small x before the hexadecimal number. That will tell you that it's hexadecimal. That is popular in Unix and C. Another popular method is to take this BC12 and place a small h to the right of it. That will also denote that that is a hexadecimal number. Now, why are hexadecimal numbers so popular with computers? Let's discuss a little bit about bits and bytes and nibbles, okay? A computer works generally on bytes. A byte is equal to 8 binary digits. 1, 2, 3, 4, 5, 6, 7, 8. So 1 byte is equal to 8 bits. A nibble is equal to 4 bits. There are 2 nibbles per byte. Now, in hexadecimal, let's take A and F. F equals 4 bits. This nibble, if it were all ones, which it is, equals F in hexadecimal. Actually, let's go ahead and place an F right here. FF, now making this byte all ones, is the maximum value that you can have in an unsigned byte, which is 255 in decimal. So that is some of the reason why the hexadecimal is popular in computer systems, because they use bytes. Hexadecimal breaks down easily into half byte sections, which are nibbles, and it makes it very convenient to use. So a little bit of extra information for you. I hope that you enjoyed this tutorial, and I'll see you in the next chapter. Thank you. Hi, welcome to this chapter of this tutorial. In this chapter, we're going to be discussing converting decimal numbers to binary, octal, and hexadecimal. Let's begin with discussing with converting a decimal number of 91 into binary, which is a base 2 number system. What you need to do is you need to take your decimal number and divide it by the base of the number system you are trying to convert it to. In this case, binary being base 2, we would need to convert it by dividing it by 2. What we will do is we'll divide 91 by 2 until we can divide it no more. Then what we will do is we will place remainders on the side, and each one of these remainders will be the equivalent in binary to 91 in decimal. So let's go ahead and begin. 9 11. And finally we have 2 going into 1, which you cannot do. So the 1 is our last remainder of 1. This is our most significant digit, or in this case, most significant bit. This is our least significant bit, or least significant digit. From bottom to top and left to right, we will put 1, 0, 1, 1, 0, 1, 1 in base 2 binary. So 1, 0, 1, 1, 0, 1, 1 in binary is the equivalent to 91 in decimal. So now let's go ahead and try to convert a decimal number a decimal number to octal. Let's go with the same number. Let's say we have 9, 1, 7, 3. This is a little messy, so let's put another 9 up here. 9. Okay. Now, I don't have enough board space to do long division, so that's typically what you would be doing with a two-digit number you're dividing by. But in this case, let's see, 9173 is, let's do it with a calculator. What I wanted to show you, I almost forgot. Since a lot of you are not going to feel very comfortable dividing by 16 in your head, you might want to use a calculator. Using a calculator, there is an additional step, which is important. So let's go ahead and take 9173 and divide by 16, and that will give us 573.3125. Now, with this remainder, we cannot convert the number like we were before, because before we had just the regular remainder right here. So what we need to do is we need to convert this fractional decimal back to its original form that we had before. So let's take 0.3125 and we will multiply 0.3125 by 16. That will give us a remainder of 5. Now the decimal fraction is null and void. We don't want to use that anymore. Now we're going to divide 573, just the whole number, by 16. 573 divided by 16. 35.8125. 35.8125. Again, 0.8125. Multiply that by base 16, or our divisor 16, will give us a remainder of 13. $35, remember we don't use this, 35, just the whole number, divided by 16 is 2.1875. 2.187 and 5. And 0.1875 times 16 is a remainder of 3. And 16 cannot go into 2, therefore we have a remainder of 2. So the bottom number here is our most significant digit. The top number is our least significant digit. From bottom to top and left to right, we will have 2, 3, D, 5. If you remember from the hexadecimal part of this tutorial, the letter D represents 13. So 23D5 is the equivalent to 9,173 in decimal. And I believe that covers all of our decimal to octal, hexadecimal, and binary conversions. So thanks for watching, and I'll see you in the next clip. Hi, welcome to the last part of this tutorial. In this last part, we're going to discuss converting hexadecimal, octal, and binary with each other. And let's begin with the binary to octal conversion. Let's take a binary number of 1, 0, 1, 0, 1, and binary. And let's convert this to an octal number. Better yet, let me change this to 111. Okay, now, luckily with octal, it is a base 8 number system, and it has the digits of 0 through 7. This 111, these 3 bits of this binary number equal 7. So in order to convert a binary number to octal is simply a matter of dividing it up into 3-bit sections, like this. Now you take these 3 bits, and you have only 2 over here, but for example, you have 3 bits, and we can convert this, which we know is a 7, and this is the first, second, so we know this is a 2. This binary number is now equal to 27 in octal, base 8. Very, very easy to convert this. As I said, break it up into 3-bit sections as far as your binary number is. Every 3 bits will equal 1 digit in your octal number. Now let's convert it to hexadecimal. Okay, now I'm going to change this. Okay, now for hexadecimal. Hexadecimal is a base 16 number system. It has the highest number is 15, which is F, and it just so happens that every 4 bits in a binary number is equal to 15, which is equal to F. All you need to do, as we did with octal, is to divide this up into 4-bit sections instead of 3-bit sections. So starting from the right, we will take the 4 bits, we will split it. This is 1 digit in our hexadecimal number, and this will be our 2nd digit in our hexadecimal number. We know that 111 equals F, which is 15. F in hex, and this number is 1, 2, 4, 5. So this would be 5F base 16. So 1011111 is equal to 5F in hexadecimal. Now let's go ahead and let's convert hexadecimal A7 to binary. That's simple, as we just did before. Split each digit up. We know each digit represents 4 bits in binary. So 7 is going to be 0, 1, 1, 1 in binary, and the A is going to be a 10. So that will be 1, 0, 1, 0 in binary. So A is equal to 10, and it is equal to 1, 0, 1, 0. 7 is 0, 1, 1, 1. Base 2, our number is 1, 0, 1, 0, 0, 1, 1, 1 in base 2. We've now converted our hexadecimal number to binary. If you had an additional digit over here in hexadecimal, that would be another 4 bits over here in your binary number, and that continues on forever. So now let's go ahead and convert a hexadecimal number, an octal number, to binary. And we will go with 7, 2 in base 8, radix 8 for octal, Each digit represents 3 binary bits. We know that 2 will be a 0, 1, 0, and a 7 will be a 1, 1, 1. Now our number is 1, 1, 1, 0, 1, 0 in binary. Very simple. So each digit, split them, convert them to their 3-bit counterparts in binary, and you have your conversion. Now to convert between octal to hexadecimal, it's the easiest way to do it is to convert them by using binary, what we just did. Now let's go ahead, I'll run you through an example. Let's take octal 72, base 8, and like we just did, 0, 1, 0, and 7 is a 1, 1, 1. And now, to convert this over to hexadecimal, every 4 bits, so 1010 is 10, which is A, and this is 3, so 3A is base 16. Hexadecimal is the equivalent to 72 in octal. So to convert octal to binary, split it up into the 4 bits and convert it to hex. It works the same way for hexadecimal to octal, and we will do that problem now. Kid B, 3. Now we know that 1, 1, 0, 0 is 3, and B is 11, so 8. So 1, 0, 1, 1, 8, 9, 10, 11 is V. So we have 1, 0, 1, 1, 0, 0, 1, 1 in binary. Base 2. Now we will split this up into 3s. There's that. There's 33 digits there. And we will convert this over to octal. So we know that this is 3. 1, 2, 4. This is 6. 1, 2. 2, 6, 3 in octal is the equivalent to B3 in hexadecimal. And this concludes our tutorial. Thank you very much for watching. And if you enjoyed it, please subscribe. Until next time, this is Martin Sigley. Catch you later.